We next discuss the boundary conditions of EM waves at material interface. Consider an interface formed by material of epsilon 1 and the material of epsilon 2. And here is the normal vector starting from the epsilon 2 and pointing to epsilon 1. And for the boundary condition, we start with the source-free problem. As we know, the source of EM wave is current density J and charge density rho. The source free means that J and rho, both items, are 0. So we start from the curl equation. For curl H, due to J is 0, curl H will be equal to partial D over partial T. And the displacement field D can be re-expressed as epsilon E here. And now we want to perform the surface integral of this equation over an open surface. Here, we define an open surface across the dielectric interface. Sorry, here it should be N hat. We define an open surface like this. Is a rectangular. The contour of the open surface is C, and the width of the open surface is dl. The length is d capital L. And now we like to perform the surface integral over this open surface. So for the left hand side, the surface integral will can be written like this: curl H dot dA. And by Stokes theory, we know that if you perform curl H, if you perform surface integral of curl H over an open surface, it will be equal to the closed line contour of H dot dl along the contour C, which enclosed the open surface S. Okay, and also the right hand side here, we also perform the surface integral. As you perform the surface integral, we can put d over dt out from here, and inside the integral will be epsilon E dot dA. Okay, now we consider a situation as dl approach to 0. As dl approach to 0 means that we pressed the upper side and the lower side to the interface. So we make the dl very, very small and almost to be 0. Due to dl is almost to be 0, the area formed by this rectangular will be almost 0 too. So the surface of this rectangular will approach to 0. As a result, we can note that this, due to S is approach to 0, the contribution of this integral will be 0. And how about this one? This one, we perform the closed line integral along C. We perform line integral here, 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 and here. Due to dl approach to 0, the contribution of these two sides is 0 too. These two sides have no contribution due to dl is 0. Then we only have the upper side and the lower side. So for this closed line contour, we have only upper side h1 dot delta L plus h2 dot. Due to the direction of these two sides are different, are in opposite direction, so this one will be minus delta capital L, and this will be 0. Okay, and as I have mentioned, as we press the upper side and the lower side to the boundary, then the h1 will almost, the delta L here will almost be the tangential part at the interface. So h1 dot delta L will become ht1 multiply delta L, and here will become ht2 times delta L. Okay, so from this result we can have the conclusion that ht1 will be equal to ht2. The same process can be applied to curl E, and you will have the similar conclusion that ET1 will be equal to ET2. So these are the important boundary conditions for EM wave. Okay, and these two equations, these two boundary conditions tell us that the tangential component the tangential components of E field and H fields, they are continuous. Making ht1 equals to ht2 and et1 is et2. Okay? This boundary condition can be written in vector form. We can rewrite it as n close h1 equals to n close h2. Also, n hat close E1 will be equal to n hat close E2. And finally, if there exists current density along the interface, what will happen to the boundary condition? The boundary condition for E field is the same, but for H field, they should be modified as n hat close H1 minus H2 will be equal to JS. Okay, so this one is the modified boundary condition as we have JS. If we don't have JS, the tangential boundary condition for E field and H field is these two equations. We next consider the boundary conditions derived from the divergence equation. For the divergence equation, we have divergence D is 0 due to source free for rho is 0. And we can also have divergence B is 0. And now we like to perform the Varlen integral of these two equations. So consider again the surface, the interface formed by epsilon 1 and epsilon 2. And then we define a Varlen. We define a cylinder here. Here is the cylinder across the dielectric interface. The surface of the cylinder, there are three surfaces of this cylinder. One is the upper surface, second is the lower surface, and the third is the sideward surface here. For the upper surface, the size of the surface is delta A, and we have the normal vector n hat. For the lower surface, we have the size is also delta A, but the normal surface of the normal vector of the lower surface is minus n hat, which is in opposite direction of the upper surface. Besides, we have the third surface is the sidewall surface. As a result, we define the height of the cylinder is dl. Okay? And now we like to perform the volume integral of this equation in the cylinder. Okay? So, we perform the volume integral of divergence D in the cylinder. And from the divergence theory, it tells us that if you perform divergence D in a volume, it will be equal to the total outward flux of the D field to the surface of the volume. So the total outward flux of the D field is expressed in this way. So the total outward flux should be perform the closed surface integral at three surfaces. One is the upper surface, the second is the lower surface, and the third is the sidewall surface. Okay? And due to the right hand side here is 0, so the integral of the right hand side is 0. And we can also have, if you perform the total outward flux of B field, the result is also 0 too. Okay, and now we consider a situation that as we make dl approach to 0. This means that we press the upper surface to the interface, and we also press the lower surface to the interface to make dl is almost 0. As a result, you can see that due to dl is almost 0, the contribution of the sidewall is 0 too. So the total outward flux will just combine the result of the total outward flux is just from the upper surface and the lower surface. So this total outward flux will become d1 dot delta A n hat plus d2 dot delta A minus n hat. Okay, due to dl is almost 0, the total outward flux just come to the upper surface and the lower surface. And we can rearrange these two. Then we will have, okay, I should write it like this. And then I can rewrite it as d1n minus d2n times delta A is 0. Okay, and also we can have b1n minus b2n times delta A is 0. And these two can give us the boundary condition of the normal component, that is d1n equals to d2n, and the b1n equals to b2n, and these are the boundary condition of the normal component, which tells that the normal component of D field and E field and the B field are continuous. Okay, so these are the boundary conditions derived from the divergence equation. And again, we can rewrite the above boundary condition in vector form. We can have n hat dot d1 equals to n hat dot d2. And also, n hat dot b1 will be the same as n hat dot b2. Besides, if we have the surface charge density rho s, Then we have to modify this equation as n hat dot d1 minus d2 will be log s. So these are the normal boundary conditions for the EM field. So please keep these four equations in mind. These are very important boundary conditions for EM wave at dielectric interface.